Hello everyone, I'm İrem Nur Tokaç and I'm very happy to present my paper titled A Declarative Human-Robot Interaction Workflow. This paper is based on and contributes to three main research fields. Human-robot interaction, specifically human autonomy teamwork, investigates collaboration between human and robot agents. However, collaboration between them is very challenging because the way us humans perceive our environment, process information, and communicate is inherently very different than the machine processes. So it is very important to establish a communication process, so to say, a common language between human and machine agents. Interactive fabrication research enables human agents to control fabrication operations on the fly. However, the impact of such interactive processes in terms of material exploration is not well researched. Material-driven design, on the other hand, explores the relationships between fabrication operations and material forms. However, the research studies mostly rely on imperative algorithms. Accordingly, I pose three research questions. How can human-robot interaction combine human adaptability and robots' computational powers for an iterative design and fabrication process? How can improvisation be incorporated into robotic fabrication to transform it into a medium for creativity? And finally, how does the integration of materiality into robotic fabrication influence design ideation? In relation with these questions, this paper contributes a declarative approach to human-robot interaction, iterative and craft-inspired robotic fabrication workflow through rule-based interactions, and a documentation of design space exploration via user studies. So, first of all, it is essential to define the robot's action and sensing capabilities. For example, one of the collaborative robots that we used in the studies is KUKA EVA, which has the capability of translation and rotation along 3 axes. It has an internal force torque sensor which measures applied force along X, Y, and Z axes. And we use this collaborative robot for sand casting and clay forming studies. Due to their malleable qualities, both sand and clay provide a medium where unexpected forms and expressions can occur and explored. Based on the robot capabilities, action and sensing parameters are defined. Most importantly, a set of algebraic symbols functions as operators. A software add-on that computes with these operators and combines sensor states with action selection is developed. This add-on works in Grasshopper, a commonly used parametric design platform in the fields of architecture and design. Accordingly, a user defines rules to combine robotic action with sensor thresholds by using this custom developed add-on. The add-on components generate the robotic action planes based on the sensor thresholds, and the generated planes are stored in a database. The external plugins convert the generated action planes into a native robot language and send to robots each time that an interaction happens. A middleware manages real-time sensor data to detect human and material feedback, then sends the detected sensor thresholds back to the database to be processed further in action selection. This video shows how simple rules allow real-time human-robot interaction in case of sand forming, where we see both material and human feedback included in the interactive process. This video shows a slightly more complex rule notation that includes both recursive and simultaneous action combinations that defines an incising stroke on the clay surface. Rule notations are transferable across different robot platforms processed with 2 different robots. This video shows How user interventions influence the robotic actions based on the given rules. Once the user pulls the end effector, the incising action is triggered, going between the points B to D, and before its completion, because previously we can see that it is completed at the point C, before its completion, the user pushed the end effector backward, which caused the end effector stopped doing the incising action, shifted, and repeated the incising at this new position. Accordingly, we have a combination of different lengths of incising. Based on the consecutive interactions, looking whether the full action is completed or interrupted, generated action planes are structurally recorded in distinct lists, which are combined into data trees. Due to the structured recording, we can specifically access the action planes at any interaction instance. For example, here a specific part of this material sketch is isolated. The toolpath of the isolated expression can then be mapped between selected positions and combining it more complex textures. Since each action parameters are known due to the rule structure, such as rotational value, the expressions can be modified by altering these parameters. Accordingly, the declarative HRI approach allows exploring the material effects by simple rules, isolating a small part to compose more controlled textures, then modifying these textures into more elaborate compositions. The applicability of this declarative HRI approach and its workflow is explored by two novices. The first participant used the simple stamping rules for sand casting, in which the robotic system received feedback from human and materials. Now you can see the material feedback over here. First, the distance between each stamping action was 50 millimeters, which led almost a grid of stamp cavities. The participant 1 then decreased the distance to 25 millimeters. As a result, the grid becomes shifted, where we can see here, as the cavities get closer, material feedback deflates the end effector trajectory more. These shifts were not planned or predicted, but rather manifested during the process. In the next step, in order to exaggerate the deflection, she decreased the distance between the cavities to 12.5 millimeters, which resulted a completely different expression composed by sand fragmentations and dispersion. The deflections are visible in the recorded toolpaths as well. Replay of the recorded toolpaths resulted in quasi-reproducing the sand patterns. Participant 1 modified the toolpath of the most complex pattern by reducing the stamping depth gradually. As the depth decreases, the sand fragmentations reduced and the geometric shapes of the cavities become more visible. Final result as bespoke sand-casted plaster pans. And a second participant, referred as participant 2, explored how to control the emergent material expressions. He started with clay forming by using stamping rules with a wooden tool. However, he changed the rules so that each stamping has a random depth between a maximum and a minimum value. Due to the depth differences, he found out that stamping actions resulted as smooth, rounded walls around the cavities in clay. He then fine-tuned the rules where these walls would be most pronounced or disappeared. Afterwards, he changed the end effector position without changing the rules that resulted in a pattern as seen in the frame F. Following that, increasing the distance between each stamping action resulted in scaling up the pattern. He then tested these rules via sand casting, where we can see geometric patterns of controlled expressions in the first 4 frames. The frames C and G show a pattern where a part is dominated by sand fragmentation due to the increased stamping depth. The user then fine-tuned the rule parameters to control these finer patterns. Finally, he applied a dynamic rule strategy where the rule parameters changed with each interaction as the pattern progressed. Finally, I would like to sum up the contributions of this research. The declarative HRI approach enables enriching the creative design space of robotic fabrication with material expressiveness. It allows materials to become active participants in the interaction, where we can see in this example, the rule-based nature allows to distinctively record dynamically created toolpaths upon each interaction instance, which we can selectively use later. This selection would be difficult by free-form hand-guiding methods where generated action points continuously recorded without any distinction. Based on the user studies, we can conclude that the declarative approach is easy to use for novice designers with some limitations. During the conducted interviews with participants, they mentioned simple interaction rules are easy to encode by using algebraic notations. However, when it comes to more complex action definitions that involves several action combinations, the algebraic notations become difficult to manually write down. So the declarative HRI approach enables any interaction process to be tested with various end effector tools and transferred to different fabrication systems. This modularity offers significant advantages for future design scenarios where humans and machines act as co-designers. Thank you for listening my presentation, and I hope to hear your questions.